Morning. This video is going to focus on the nerve impulse. It's going to focus on the electrical portion of neuronal communication. Again, neurons communicate electrochemically, and we will focus on the electrical portion today. So we're going to start by discussing the membrane potential, what it is, how it's measured, and why that's important. So messages in a neuron develop from disturbances in the resting potential. When a neuron is at rest, the membrane, the fatty proteins that surround the cell maintain an electrical gradient known as polarization. And so there's a difference in charge inside and outside of the cell. And the inside of a cell is more negative compared to the outside of a cell. The resting potential is negative 70 millivolts. Again, that's describing polarization, the difference in charge from the inside and the outside of the cell. And we can measure the activity of a neuron by inserting an electrode into the cell and having a reference microbe outside of the cell. Now, like I said before, the inside of the membrane is slightly negative with respect to the outside of the cell. So it's approximately negative 70 millivolts. That's the resting potential of the neuron. And that's the state of the neuron prior to sending a nerve impulse. The resting potential of the neuron is important because it readies the neuron for quick response when messages are received from the presynaptic neuron. So it readies the cells to respond quickly to incoming information. Okay, so there are factors, ionic factors, that contribute to the even distribution of ions, and ions are charged particles. There are two forces that are working to move ions inside and outside of the cell. And ions move because membranes are selectively permeable. So some ions, chemicals can move freely inside and outside of the cell through protein channels, and some ions can't move freely. They have to have channels that will open up to allow them to flow. Now, there's random motion of ions, and particles tend to move down their concentration gradients. So they want to move away from where they are more concentrated. Electrostatic pressure also influences the movement of ions, right, or an electrical gradient. So in terms of ions, opposite charges attract. So positive repels positive, but negative ions want to move towards where there's a positive charge. Like I was saying before, the membrane is selectively permeable to ions. So again, some ions can move freely inside and outside of the cell through protein channels or gates in the membrane. Some ions can only move through channels that are voltage gated, and they open or close depending on the charge within the cell. So when the membrane is at rest, ions move in and out through ion-specific channels. So we have some major players here. I'm going to introduce you to them, and then we're going to focus on potassium and sodium. Okay. So when the membrane is at rest, we have chloride, which has a negative charge, and it just moves freely inside and outside of the cell. That ion channel is open. The potassium channel is somewhat closed. It's mostly closed, but some potassium ions can move in and outside of the cell somewhat readily. Now, importantly, there is little movement of sodium. Those channels are closed. There are some negatively charged proteins that are synthesized within the neuron. They're found primarily within the neuron, and they're trapped inside of the cell, which again helps keep the polarization for the resting potential. Okay. Again, we are going to focus primarily on potassium and sodium, and it's important to know that the gate for sodium is closed, and for potassium, there's a little bit of space to allow potassium to flow. Here is a figure showing a protein molecule or an ion gate or channel. Okay, so again, we're going to, chloride stays at an equilibrium. Channel is open, it's going to move freely inside and outside of the cell, and the concentration of that chemical is balanced inside and outside of the cell. So chloride is at an equilibrium. So let's not talk about chloride for now. You really want to talk about sodium and potassium. And I talked about before the forces that work to move ions. We have the concentration gradient, and we have the electrical gradient. So there are two forces that move ions. Okay. Now, so let's take sodium first. And remember that the gate for sodium is closed. Now, sodium ions are more distributed outside of the cell than inside of the cell. Right? So there's not a balance of their distribution. They are more concentrated outside than inside the cell. Okay? Now, the concentration gradient wants to move an ion from where it's more concentrated to where it's least concentrated, right? So the concentration gradient is working to move sodium inside the cell, right? But it can't move inside of the cell because the gate is closed. Now, the inside of the cell is more negative compared to the outside of the cell. Sodium is a positive ion. It has a positive charge. So opposites attract. The electrical gradient also wants to move sodium inside the cell, right? So we have two forces wanting to move sodium inside of the cell. It's quite a bit of force or pressure trying to move those ions inside of the cell. And again, it can't move inside because that gate is closed. There's a few that get in, but not very many at all. And we have a sodium-potassium pump that is exchanging sodium ions for potassium ions. So this sodium-potassium pump, it's an active process. It takes energy to move these ions inside and outside of the cell, but it's continuously moving 3 sodium ions out of the cell and 2 potassium ions into the cell. Okay, so those bits of sodium that get in the cell are being removed by the sodium potassium pump. Okay. So potassium, on the other hand, potassium has a positive charge. And again, the inside of the cell is more negative as compared to the outside. So the electrical gradient wants to move potassium inside the cell, right? Opposites attract. Negative inside, potassium's positive. Electrical gradient wants to move it inside the cell, right? Now, potassium is a little more concentrated inside the cell than it is outside of the cell. So the concentration gradient wants to move potassium out of the cell. So these forces are working in opposition. One wants to move potassium inside, the electrical, and the concentration wants to move potassium outside of the cell. So potassium is kept relatively balanced, and the sodium potassium pump bringing some potassium inside of the cell. The gate's a little open, so some flows out freely. The sodium potassium pump will bring it right back into the cell. So potassium is pretty much balanced. So again, and this is a figure that shows the movement of the ions through the gates, the direction of the movement for each of these ions. And here's a video that will help describe all of that. Now again, the nerve impulse is going to be influenced by the change in the membrane potential, or the change of the charge within the cell compared to the charge outside of the cell. Now, to have this be a little more understandable, the neurotransmitters, right, that are housed in those presynaptic terminal buttons that I talked about in the previous video, the neurotransmitters are the chemical messengers that influence the charge within the receiving neuron. Again, the site of receiving information is the dendrites. So neurotransmitters attach to dendrites and they influence the charge within the cell. You could also influence the charge within the cell by using an electrode and sending some stimulation. Now, there are 2 types of messages that a cell can receive. One message is it's excitatory. It will make that cell more likely to communicate a message to the next cell. And that's called an excitatory postsynaptic potential. And again, it's a message that's going to change the voltage within the cell, okay? And an excitatory postsynaptic potential is going to decrease the polarization, or it's going to move the charge inside of the cell to become less negative. It's going to move it towards 0. 0 would be no polarization, no difference in charge between the inside and outside of the cell. So excitatory postsynaptic potentials change the voltage inside the cell, and it becomes less negative. This is also called a depolarization of a cell. Okay? So this little increase up here, lost my mouse, there it is. This little bump here is a slight depolarization. The inside of the cell is moving towards 0. In Inhibitory postsynaptic potential means a cell is receiving inhibitory information. It's going to make that cell less likely to fire or send its message down the axon, right? Remember, that's that thin fiber where the message is transmitted. Inhibitory postsynaptic potentials makes the charge inside the cell more negative, right? So it hyperpolarizes the cell, less likely to fire. So depolarization, the cell is receiving excitatory messages, it's more likely to fire. Hyperpolarization, right? The cell is becoming more negative relative to the outside, and it's less likely to fire or send a nerve impulse or an action potential or its message down the axon. Okay. Now, a cell has to receive enough excitation in order for a nerve impulse to be generated. Okay. If a cell receives enough excitatory postsynaptic potentials, there'll be a rapid depolarization of the cell, right? So the charge is moving near zero, it's past it, and it sends its message. And that is called the action potential. As you can see at the end of the action potential, we'll talk about this in a moment, there is this dip or this hyperpolarization that happens at the completion of an action potential. Okay. Here's another video that you can watch on your own. Okay. So one excitatory postsynaptic potential typically will not cause a neuron to fire or to release the neurotransmitter. There's summation that is needed, or multiple signals that a cell is receiving. We're going to talk more about that next week, what summation is, and the different types of summation. So, in order for an action potential or a nerve impulse to generate, there's a threshold of activation that needs to be reached. Okay, so let's go back here for a moment, right? So this little bit of excitation, this little bit of depolarization is not going to produce an action potential. We need enough stimulation that we reach what's called a threshold. And the thresholds are different depending on the neurons, but it's approximately negative 65 millivolts. So again, the neuron at rest is negative 70. It receives excitation that changes the charge inside the cell relative to outside of the cell. It becomes less negative, it depolarizes, it reaches about negative 65 to negative 45 millivolts, and that's its threshold. Once it reaches that point, there's a rapid depolarization, right? So you can see this peak, right? The cell becomes less negative to the point where it moves over zero, and the inside of the cell is now more positive than the outside of the cell, okay? It reaches that peak that you see, keep losing my mouse. It reaches this peak, and an action potential is generated, right? So an electrical message is sent down the axon at this point, okay? It fires, the nerve fires an action potential, or it sends a nerve impulse or an electrical message down the axon, okay? The site of activation is the axon hillock. Okay, so messages that come from the dendrite have to reach the axon hillock in order for the charge to change. Okay. So again, that threshold here on the slide, it says negative 65 millivolts. It ranges depending on the neuron. The peak of the action potential, the peak of depolarization changes depending on the neuron, but it's approximately negative 65 millivolts. Now, again, this cell is receiving inhibitory and excitatory messages. So it needs to combined still reach negative 65 millivolts in order to generate an action potential. There's that threshold. Once it reaches that threshold, rapid depolarization message is sent down the axon. Now, action potentials follow what are called the all or none law. They either happen or they don't, right? So we either get to the threshold and the cell fires, or we don't reach threshold and those signals will just degrade, okay? For each neuron, when an action potential is sent, the speed of that action potential, its velocity, and its magnitude remains the same. It's independent on the intensity of the stimulus, okay? So once the threshold is reached and that nerve fires, that message is transmitted at the same speed and magnitude every time for that neuron. So it either fires or it doesn't, and if it does, same velocity, same magnitude. Doesn't matter the intensity of the stimulus that caused it. We get information about intensity of a stimulus based on the pattern of firing and the rhythm of firing, right? So it's like, how often is that neuron firing? Not the speed of the message down the axon, but how often is an action potential being sent? That will tell us about intensity. Patterns of timing and rhythm. Like I said before, the action potential begins at the axon hillock. It's the little bulb in between the cell body and the axon. There are dendrites that are coming into the cell. Some of the dendrites are closer to the axon hillock. So information that comes in closer to that area will have a bigger impact. Messages that are received further away from the axon hillock, there's some degradation by the time that message reaches the axon hillock. But again, summation is important. If the voltage changes to the threshold, the message will be sent. Okay. We will talk about neural integration next time. So how summation happens, we'll talk about that next time. But again, there's this combination of messages that will depolarize, messages that will hyperpolarize, and it's a culmination of these messages. Okay. So let's talk about what happens for sodium and potassium during the voltage change and the action potential. Okay. Okay. So the cell is receiving excitatory messages. Okay. Once that threshold of negative 65 millivolts is reached, the sodium gated channels are going to open. Now remember, there are two forces that are working to move sodium inside the cell. So sodium is going to rush into the cell, and that's what causes that rapid depolarization that we saw in that graph. Now, when the rapid depolarization happens and we get to the peak where the action potential is sent, the sodium gates are going to close. So there's all this sodium that's left in the cell, which changes the inside, it changes the polarization. Okay, so now the inside of the cell is becoming more positive. Now, at slightly after the sodium gates open, the potassium gates are going to open. Potassium processes work slower than the sodium processes do. So the potassium channels slowly open, right? Because sodium has changed the polarization and the inside of the cell has become positive. So potassium is going to move out for its concentration gradient, but also its electrical gradient. Because the sodium channels close slowly as well, and now there are two forces moving potassium out of the cell becomes slightly hyperpolarized, which was that dip that I showed you in the other figure. Okay, so we have our threshold of excitation. Sodium channels open. There's forces just pushing sodium in there, can't get through. So when those gates open, it's like whoosh, right into the cell. Okay. As you can see, the potassium channels open slightly afterwards, but the inside of the cell hasn't become positive yet. So, so potassium is still kind of flowing pretty freely. We get to the peak here where the action potential is sent. The sodium gates close. Now the inside of the cell is positive. Potassium channels have not closed yet. So here we have potassium leaving the cell. And again, it's leaving the cell because it's more distributed inside, it's more concentrated inside than outside. And now the inside is positive, so positive potassium wants to move out. The sodium that's in there is stuck in there for now. Right? All this potassium is coming out. It hyperpolarizes the cell. This is an important period. We're going to talk about this in a minute, right? But it's slightly more negative than the resting potential over here. Okay? Now, after these channels close, and they still have this little gap, some more potassium is flowing out. Now you have the sodium potassium pump that's going to restore the cell to negative 70 millivolts. Again, it's going to bring sodium out, 3 ions, and replace it with 2 potassium. 3 out, 2 potassium in. This takes a little bit of time. So the cell stays hyperpolarized for a little bit of time. This hyperpolarization of the cell is called the refractory period. And this is an important period of the cell's process. The absolute refractory period only lasts about 1 millisecond. This is a point in which it doesn't matter the intensity of a stimulus, that cell cannot fire, cannot send an action potential. The relative refractory period is about 3 to 4 milliseconds after the absolute refractory period. During relative refractory period, the cell can fire, but it needs more excitation than it normally would. So stronger than usual, than there's just strong stimulus could make it fire. So you can understand the refractory period by thinking about flushing a toilet, okay? The toilet's just been flushed, that's like the action potential. Doesn't matter how hard you push that handle down, the toilet won't flush again. That's the absolute refractory period, right? Doesn't matter how hard you press that handle, how intense your pressure is, it's not happening. But during the relative refractory period, right, there's that moment in time where, you know, you hold it down a little longer, you push a little harder, and the toilet will flush. That's like a stimulus causing an action potential in the relative refractory period. So now, every time that toilet flushes, though, right, it's like the same amount of water, the same amount of speed. That's kind of the all or none law, right? So it's the same speed, same magnitude each time. Now, what I said before, we know about the intensity of a stimulus that causes communication based on the timing of that neuron. It's like a rapid firing over and over and over again if there's a strong stimulus in the environment, right? Pushing that handle down even further is not going to change the actual flush of the toilet. Or, you know, if I want to turn my light on and I use a lot of force, the light's not going to get brighter, right? But if I, you know, on and off, on and off, on and off with the light switch, that's a pattern of communication. So it's the timing or the pattern or the rhythm of neurons firing that gives the nervous system information about the intensity of the stimulus. How hard is the touch? How bright is the light? How loud is the sound? Right? Sorry that I'm clearing my throat in a video so much, but anyway. Okay, so let's talk a little bit about axons and the conduction of an action potential. So not all axons are myelinated, right? So myelin is that fatty substance that insulates an axon, but not all axons have myelin. Now for unmyelinated axons, or just axons in general, the way that the axon potential is conducted is that there are sodium gates along the axon. So the impulse regenerates at points along the axon and it kind of flows down like a wave, regenerating. Okay. When the sodium gets diffused, the next, there's a channel that will open and it triggers the next portion of the action potential. Now, because of this type of regeneration, the message flows down an axon in a single direction. At the start of the action potential, there is some of the message that transmits towards the cell body. Now, there are some neurons, like local neurons, that don't have axons at all. So the message doesn't flow down an axon. They just communicate with their neighbors in a slightly different way. So the refractory period, both absolute and relative, plus this, the propagation of the action potential, how there's regeneration points along the axon, keeps it flowing in one direction. Now, in myelinated axons, there are no sodium channels beneath the myelin. Those sodium gates are at the nodes of Ranvier. So an electrical impulse travels quickly through the insulated part and regenerates at these nodes. And it's like, they call it saltatory conduction, and it's almost like it's jumping from point to point to point. This creates a faster transmission. So myelinated axons send their messages faster than unmyelinated axons, okay? But again, each neuron sends their message at the same speed. It can vary between neurons, but it's the same every time for that neuron. The myelinated axons are faster transmission, and they require less energy because of the distribution of sodium channels, which again, that's an active process to open protein channels and close them, and the sodium potassium pump has to reestablish the electrical charge. So it requires less energy. Larger neurons have faster communication than smaller neurons, and myelinated axons are faster than unmyelinated axons. Again, conduction of neurons without actions, the transmission is graded and decremental. So excitatory messages can decrease, they can fade away, and the message is bound to the intensity of the stimulus. So it's not an all or none law. The intensity and the transmission are intertwined. Local neurons or intrinsic neurons don't have axons, and they communicate in this way. Now, I already talked about saltatory conduction, right? It's like the jumping of the action potential from node to node, or gap, the node of Ranvier, right? The gaps in the myelin. Multiple sclerosis is a disease in which the myelin sheath is destroyed. And so what happens is that nerve impulse doesn't get regenerated because there's no sodium channels where the myelin was. So the strength of the electrical message will just degrade. It won't reach its target. Therefore, that neuron will eventually die because it can't send messages. Use it or lose it. Okay, so here's just a fuller discussion of a local neuron, right? So they have short axons or don't have axons at all. They exchange information with their close neighbors, but they do not produce action potentials, which is the communication we were predominantly talking about. So they produce graded potentials. So it varies in magnitude related to the intensity of the message it's receiving. It does not follow the all or none law. Again, the all or none law, when a neuron fires, that neuron will fire with the same velocity and magnitude every time, independent of the intensity of the stimulus. So it depolarizes or hyperpolarizes local neurons, depolarize or hyperpolarize in proportion to the stimulation, right? So depolarize, excitatory, hyperpolarize, inhibitory, excitatory, depolarize, more likely to communicate with other cells, hyperpolarization, inhibitory, less likely to communicate with other cells. Local neurons, interneurons, they're difficult to study because they are small. And if you put an electrode in a small cell, you could destroy it. So most of the knowledge that we have has come from studies of large neurons. In fact, some of the earliest studies where the velocity of a neural impulse came from the neurons of squids, which have much larger axons than our nervous system has. This fact that local neurons are small and they're therefore hard to study, scientists used to think they were underdeveloped neurons. That could have led to the myth that we only use about 10% of our brain, which is entirely untrue. I also think people like that myth because it allows, I have all this unmet potential because I'm not using my full 90% of my brain's not being used. No, your whole brain is being used. Your whole brain is not firing all at the same time, but you are using all of the networks that you have in your brain, or you wouldn't have those networks. They would prune away and you would form different synaptic connections, right? There's a high metabolic cost of the brain. The brain is only a few pounds, but it uses most of nutrition to keep the brain functioning. So you do use all of the brain. So let's dispel that myth right now. Great, so that is the electrical portion of electrochemical communication of the neuron, and we'll talk more about that next week.